record. So what we're going to do today, as I mentioned last week, is we're continuing the pulley conversation, but we're going to have kind of like 3 steps to today, and then we're going to talk more about exercise technique. And if we don't get to the exercise technique stuff today, which I'm sure we will, but if we don't, next week we will is it next week? Yeah, next week I believe is the same Wednesday. Yeah, so next week we'll be going over rowing technique and talking about different ways to capitalize on a machine like this or a traditional cable row machine when you have access to one, to kind of focus on a minute. I think we're going to talk a little bit more about hypertrophy again, but then also talk about strength development. If you're a strength athlete, or you're someone that's looking to work on aggregate output, things that you can do to optimize this machine. Especially, I think everyone in this circle has access to. Michelle and Chris, do you guys have one of these?
We got a MedX row.
Okay, so way cooler and way nicer. So everyone's got access to a row, and I think that these concepts will extend to the Nautilus Nitro row that we've got. We've got the Strive chest support one that we'll do, a cable machine, or frankly, any version of a rowing machine. So, sorry, if someone leave I'm just gonna check the chat here quickly to see what that was. Okay. Okay, so we're gonna start off by doing a very quick machine analysis. And instead of doing the entire study group like we did with the pull down machine, I'm gonna try to walk through this at slightly faster pace, only because I wanna try and get the gist of the information like we were talking about before, but that way we can be as practical with it as possible. So now I don't wanna blow over anything that anyone wants to talk about. So as we're going through this, if I start talking about one specific point and you have a question, I'm a little further away from the camera so I can get everything in the view. So instead of typing it, please just interrupt me. Just say, Brandon, I've got a question, and let me know, and we will we'll go down that path. So this is a compound row. It is basically a machine variation of the traditional cable row that you see in most gyms. Most gyms do not have a machine that looks like this with all the mechanisms that we've got going on up here, because this machine is taking that idea of the traditional cable row, which you have all seen in almost every personal training certification course. I believe I've seen a version of that machine. At least it's been a while. This machine takes that exact same concept, but then it adds all of these mechanisms up at the front to help to manipulate the resistance and how much weight you experience throughout the excursion of the exercise to help you get a different experience. And in fact, if I had more space, I would love to have this machine right beside a traditional cable machine, so you guys could, so anyone who is exercising could get the experience of both, but also it would be great for a teaching example to go back and forth between the two. Like we talked about last week, we have very similar mechanisms that may be just slightly off frame, where I've got a weight stack and a belt coming off of it. The belt coming off of the weight stack helps to redirect the force. So all it is doing is changing the direction or creating the opportunity for the change in direction of where that weight is being expressed as resistance. At the top of this machine, which is all facing here, which is much like the pullover machine up there where there's the Nautilus Nitro bits, there are 2 pulleys which are helping to redirect the force down into the machine mechanisms here. Now, the reason why I want to talk about this machine is because we've been talking about some mechanics. And you guys will notice a couple things. This machine, although seeming very simple in mechanics from a technique perspective, right? It's a rowing exercise, which there's a lot to unbutton there, but everyone, almost anyone who's a recreational exerciser has done some version of a rowing machine. But this machine is slightly more complicated than just even a single axis machine, because much like we talked about with the row, if you look down at the bottom down here, here, and here, this machine has 2 different joint axes in which there's some pivoting happening around. So we spoke when we did the pull down that we're doing more machine analysis, again, more as an expansive exercise, as we want to identify which of the joint axes that are connecting to the resistance is closest to the weight stack, which will be our initial center of the universe, so to speak. And the reason why I would say that is that initial axis is going to allow us to compare, contrast the resistance versus effort. And in this case, we're going to do it in 2 positions, the starting position and then the end range position out here. It gets tough. Not a lot of machines have multiple joint axes like this, but Nautilus at this time with the Nitro machine did choose to do that with several machines, which allowed for a little bit more manipulation of the resistance and getting really creative with the weight stack. So unfortunately, the only disadvantage of having a very cool black on black facility, as I've said before, and wearing black pants apparently, is that I've got all these different machine parts down here that are dark and a little bit difficult to see. But what I'm hoping you can see is that I have this cable here. This cable connects into a pulley on this side, and that pulley has, as you guys can see, two belts that are coming off of it and coming into this system down, pardon me, into this system down here. Now, what gets me excited about this example, growing off of last week's example, is that we're now getting into that pulley system where we're talking about a doubler pulley. Pardon me for 1 second. Just pin this there. Okay. So if we start playing with this moving of this big system a little bit where the machine comes into it, you guys can probably see that right here is the closest post with the closest joint axis towards the weight stack. And as we were discussing with the pull down machine and for our machine analysis, we're looking for two things. We're looking for resistance and effort. Resistance is going to be the side of this axis closest to the weight stack, and effort is going to be the furthest away from the weight stack, closest to the exerciser, who theoretically would be sitting on this seat. So like we talked about with the pulleys, we have this thing right here that is a pulley, and this pulley is connected to this cable coming all the way down, and this pulley has two cables coming off of it, 1, 2. So whenever I move the machine, before we talk about moment arms, you guys probably can see it if I get a little bit further down here, yeah, is I've got these two cables that are being yanked on concurrently by this pulley when I move the weight stack. So last week we discussed with the pulleys that initially a cable coming off the weight stack is merely translating that same numerical value of force through the cable. So in this case, the lightest weight that I have on this is 20. And that means that the weight of the cable, if I were to yank on it, is also going to be 20. And all the other pulleys that we have going through this are going to be 20 and 20 until we get to something like this, where now we have multiple cables coming off of one attachment. So we found that when we were doing the halfer pulley, that we could look at the number of cables coming off the pulley and divide that to figure out how much resistance we were getting. So on the Nautilus Freedom Trainer from last Wednesday's video, we saw there were 4 coming off it, which means if we had 20 pounds, we were actually only experiencing 5 pounds in each handle. This is a little different. And that's where I said last week that that doesn't always work. It works well for halfer pulleys, but now what we have is this pulley is yanking on these two cables. We know that this cable here weighs 20 pounds, and this cable below here also weighs 20 pounds, which means that if this pulley is yanking on both cables at the same time, that means that we're experiencing 20 pounds twice. That means that this is what's called a doubler pulley, and this pulley makes this point of contact weigh 40 pounds. Newton's law of reaction force, the third law, describes that at any point that there's force expressed on a system, that there's an equal and opposite reaction force. So if we forgot about this pulley for one moment, and it's very difficult to see, but right here into this metal piece here, we have the cable going from the weight all the way through all these pulleys to that point right here, drilled in, bolted onto the machine as an anchoring point. Just like a boat with its anchor in the water, if the boat's trying to accelerate with 100, I don't know actually how the boat stuff so well, but if it's going so fast forward in the water and it's getting stopped by the anchor, that means there's at least the exact same amount of force to meet that boat with its acceleration at the anchor point. That's the same thing here. 20 pounds being distributed through all these systems. And at this point right here, that is also 20 pounds, which means that this anchor weighs 20 pounds, which means if we've got 20 pounds and 20 pounds, and this pulley is pulling on both of those scenarios, the weight and the anchor, that means that we're going to experience 40 of those pounds. Does that make sense? Does anyone have any questions about that? Okay. So This is a pulley and mechanic scenario that's very common to see in a calf raise machine. Most calf raise machines, because a lot of people are putting a lot of extra weight on it, a lot of resistance, they'll put a doubler pulley in this scenario, so that way they don't have to shift as much weight. And like I was describing with our Nautilus shrug machine, that was something that Arthur Jones did at the very beginning as well, because a lot of people can shrug a lot of weight, especially the football players he was marketing to at that time. So we had that huge crazy cam with the doubler pulley. Okay. So moving on, the reason why we have to bring that up, that works out kind of well. The reason why we have to bring this up is because we're going to get some weird number changes that are going to happen right off the bat. It's not going to be a 1-to-1. It is now a 1-to-2. It means every time we see movement at this point, at this axis, that number is going to be 40 instead of 20. So leaving that alone, I'm going to briefly do the measurements of two different parts here as we described to figure out the starting position of this, comparing the resistance to the moment arm. So the easiest way to do this, I would say, if you're not comfortable with examining moment arms, we've talked about it a lot. I would say get really comfortable with finding the joint axis, where the line of force is, and creating that perpendicular relationship to that system. If anyone wants to do a review on that, please let me know, and we absolutely can. What I would say is if you're trying to do machine analysis or you're doing exercise analysis with your partner or someone at home, measuring tape is the easiest way to be consistent. A good quality measuring tape is pretty rigid, which will allow you to get a good, accurate measurement that you can write down for the sake of analysis. So what I'm going to do is I'm going to start off with the resistance, because the resistance is the closest tied to the weight stack. And I'm going to take this measuring tape. We're going to go down to the joint axis, put it right in the center of the joint axis. We're going to go to the middle of the pulley, where there would be a 90-degree relationship. And in this case, it is 18 inches. We have an 18-inch moment arm of resistance at the starting position. And if we want to try to speed up this process, and this is one thing that I definitely do when I'm trying to prepare for a class for one of these things, is I'll put it to the extreme and I'm going to record. Now, this is obviously the very far extreme. I'm going to calculate the resistance again in the lengthened position or the long position, just to see where we're at. So same thing. I've got a joint axis. I've got these line of forces here. This is kind of a weird example. What we want to do is find the middle of these two pulleys, which is going to be our line of force, because we have of these two cables. They're pulling on that pulley, and there's a resulting force in between those two. Now we're going to put my measuring tape right in the middle here, and same thing, measuring tape, going to create a 90-degree relationship. And at this case, at this point, measuring it upside down, it's 12 inches. So we're already seeing some changes in the resistance at the very first point. So starting position is 18 inches, and then the resistance is 12. Go back, we're going to remeasure the effort and see how that is. Exactly the same. So effort now, right? That one is the resistance because it's on the side of the joint axis. Effort, we have the part that is closer to the human. That's the easiest way to recall it, is when you're looking at one of these center of the universes, you want to make sure the resistance in most cases is on the side leading to the weight stack. Sometimes that's different. On the other side, the effort is closest to the human. So the effort here is actually kind of interesting. We're getting into something called a 4-bar linkage system, which we'll save for a squat discussion day. But we've got this bar right here, which actually is how the effort is translated into this system. So when I pull on this, you guys can see this metal bar right here, pardon my pale finger, there we go, is what's pushing that posterior or that further away lever system into the front lever system, allowing the motion and the resistance changes to happen from the mechanism. So although it's a big metal bar, it is a part of the system. And in this case, that is the effort, which is weird, but makes it easier. It actually makes it easy to see that there's only two things coming off of this peg, the resistance and that which will be measured as the effort. So same rules. I'm going to find the joint axis. I'm going to come over this a bit more. I'm going to find the line of force in the joint axis. I put this at the middle joint axis, put the measurement tool that I'm using to the center of the joint axis and over to the moment arm. And in this case, this is 11 inches at the starting position. And then the end position, whoo, drops off a lot, right? So this is where it's weird. So just in case, if you guys are ever trying to do these analysis, we do need to extend that line of force where it's not over the joint axis. Because if I put this over the joint axis and I try to create any sort of perpendicular relationship, there really isn't one. So what I'm going to be doing here, just for the sake of visualization, in any course that I teach this, we have somebody help. I'm going to extend the line, which is going to help me see that the line of force is going to be to about here. Sorry, I'm trying to use the camera. There we go. Which is going to be about 7 inches. 7 inches. So right off the bat, the initial conclusions that we can make off of the first joint axis, resistance has the advantage in 2 ways in both positions, right? The starting position, resistance has a moment arm of 18 versus the effort of 11. Oh, sorry, someone's just signing in late. Okay, the moment arm of resistance is 18 versus 11. So we do have this advantage by about 50%, where resistance is bigger than the effort side of things. Concurrently, we have that doubler pulley, which is doubling the resistance, and where effort doesn't have any mechanisms that's manipulating the resistance. So at this point, this first center of the universe, resistance is
Brandon, you're blank.
winning. Resistance is it blank or is it that I'm not pinned? Can you guys see me?
Yep.
Michelle can see me.
Yeah, I can see you.
Okay.
You're just not
Scrolling.
pinned, yes.
Okay, now I
Oh,
can.
I see. Yeah.
You can see me? Hey,
Yep.
Ma, can you see me? Okay, cool. So at the very first joint axis, resistance is winning in 2 ways. Even as we go through the greater excursion, we still have that similar trend where we have that moment arm at the very end position of resistance of 12 with effort versus 7. So throughout this whole first system, resistance is winning. Now we have to stack that on top of the second joint axis. Now, very quickly, I don't want to just tell you guys the answer here, is if I have my arms out in front and I'm pulling in to perform a row, and I wanted a balanced profile from an exercise, what is the strength profile doing if I'm doing this with the combination of my muscles versus moment arms? Do I have a greater ability to produce more force here or produce more force back here?
So you have the ability to produce more force when your arms are lengthened in the lengthened position and where the resistance is higher. And then as you move back, the resistance drops off into the shortened position.
Yes. So now in this position, this is a relatively extended position for this exercise. But if we're thinking about larger muscles like the lat, this is actually a relatively mid-range position for that muscle. So that muscle has a high mid-range positions for strength curves. We know those muscles can produce the highest amount of force. As well, if I have a straight line of force from that machine to my arm, there's not much torque up and down. I don't have much resistance by the position of the machine. So both from a muscular perspective and a mechanics perspective, using a machine like this, I should have a lot of advantage at this position. And then I should be getting weaker and weaker as I come back, because again, concurrently, I have the increasing moment arm of my elbow getting further away from my shoulder, dropping off a bit, still staying pretty far away, and my shoulder extensors at all, most of those muscles, teres major and lat, all getting shorter and shorter. So not saying that we want it, but if we wanted an exercise profile that matched my strength profile or strength curve, something like this, I mean, it might be okay just if we could use that first axis, because resistance is winning. That's just showing that it's efficient for the resistance side of things. But at the same time, the resistance and the difference between a resistance and effort resistance is dropping off just a little bit as we go through this. So it's not a massive change, but it's close to favorable to what we would want. So anyway, when we talk about adaptations, we're going to come back to that curve. So just recall that when we're doing this, you got a lot more force production here and a lot less force production here in a normative row exercise construct like this, not talking about like barbell rows and things like that. So before I go on to the next joint axis and kind of go through that again at a relatively moderate pace and then talk about the mechanics, and then we'll use the dynamometer. Does anyone have any questions about that? Is there anything that stands out? Cool, okay. If anyone, like I said, if anyone does, please don't type it. It's hard for me to see the screen from here. Just shout out, Brandon, I got a question. Okay, so we're going to move on to the next joint axis. So like we talked about prior to this with the pull down machine, this joint axis is the closest to the weight stack, so it is the center of the universe. If I take a step forward and I come to this pulley here, this axis here, this is the next center of the universe. And again, how I'm describing that is that when the machine is going through a displacement, the reason why I would call it the center of the universe, much like the sun, is everything is revolving around it, which means that since that's the anchoring point, all those points of application around it, close to resistance and effort, are the things that are making the difference. And that's the piece that's helping to translate it. So now that we finished this, we're going to call that a fixed piece of information. We'll just put that on the bookshelf and come back to it. Now we're going to go down to the next axis. So again, I'm going to use the same measurement. Now, the thing that happens, like we saw with the pull down, is that this metal bar now is switching its role, right? On this side, when I'm pulling, this metal bar is pushing into this bar that translates the effort into the resistance. Sorry, when I'm pulling this, I'm pulling on this. Now it's changing that I'm actually holding the effort side of the equation, and this bar here is actually the resistance pulling on this bar to make all those resistance properties change. So it's now changing its role. So this is weird because this piece is both effort and resistance context specific. So I'm going to use that same measurement tool, get those numbers, and then jump on from there. I've got the joint axis here. If I take this metal, this is so hard to do looking back and forth to you guys. There we go. If I've got this metal bar here and we come down to this joint axis, I'm going to measure the moment arm of effort or resistance at this point. And at this point, the moment arm of effort is 7.5. I'm going to write it down as 8 to make my life a little easier, just for this example. And if I take the same system, I'm going to drop it all the way to the most extreme position that the machine can explore. And I do the same measurement. This is a lot nicer because now this bar is much closer to this joint axis, which makes life a little bit easier to measure. Same kind of idea from the joint axis to the center of that pin, and that's 5 inches. So again, seeing kind of a similar trend that as we go through this massive excursion, no surprise based off how this is looking, resistance is kind of slightly dropping off at this point. But this bar, there is no doubling effect. The doubling effect that happened up here is merely being translated to that bar. Now, getting into the effort side of the equation, we start reintroducing some variables. You guys wait, time out?
I got a quick question, Brandon.
Yeah.
So when we're now looking at this axis closest to the foot plate here, right? Yep. And you measured resistance coming up to that side of the bar because now becomes resistance.
Correct.
When you brought it all the way to the extreme end to get the smaller, the second one. Yeah. We now went to the bar closest to the machine on this 4-bar linkage here.
Yeah.
Why did we switch from that one as opposed to the axis closest to the human? Is that because we were just drawing that line of force, because it extends out? Is that why?
Was that what I just did right now?
Yeah. So when you came back, your second measurement, what was it? 5 inches.
Yep.
Is to this, that bolt that's closest. Yes. So why did we switch it to that bolt versus that first bolt that's closest on this to to the foot pedal there.
Oh, no, hold on, let me just make sure that didn't make, it's a little weird looking back and forth. I don't know if I may have made a mistake there. Let me just double check. No, okay. I think it's just a matter of perspective there, Chris. So what I did is I'm using the same joint axis.
Right.
It is the one closest to the human. It just looks a little weird because I have to extend this bar out
Right.
forward to get over top of this joint axis.
Gotcha.
But that other axis is actually still back here. So I haven't gone back to that one. It's still the same joint axis.
Okay. And then
So
it's
if
just,
I measure,
and it's just taking that force. So now if you pull the to the extreme end there,
yeah,
and then you're going to measure it, you're just taking that line there and you're just extending it up more.
that's correct. So let me be like really demonstrative with this. So if I've got this bar here and it's pitch black, so that's not helping anybody. All right. So if I just put this yellow line on the moment arm, or sorry,
Yeah.
if I put this yellow line on that bar, it's not over top of the joint axis. So if I drew a 90-degree relationship, it's not quite there. If I extend this, now we have that 90-degree relationship. So,
Okay.
and this is the same thing when we're measuring like a bicep curl moment arm, is that if I were doing a moment arm for measuring a bicep curl, right, if I'm holding a weight here and I've got this line of force that's going down from this position of a bicep curl, I don't have a moment arm to that line. So I've got to extend that line up, an invisible line, to help me see where that moment arm is. Does that kind of make sense?
Yep. Got it.
It's Peter, one of our mentors, used to say that line of force, I mean, this is not true. He said this to someone who studies physics, they'd punch you, but you could just extend that line of force to infinity. Like you just make it as long as you need to. So that way you can measure it, because if I do that same position here and I extend that line up, I can use that for shoulder, elbow, all these other joint systems.
Gotcha. All right. Makes sense. Thanks, man.
Yeah. And I say, honestly, I never took into consideration black and yellow when I was starting to prepare the study group stuff. So if this progresses on, I'll probably get some green screen. I don't know, but hopefully it'll make it look a little more clear because it is a little muddy down there. Does that clear that up?
Yeah. Thanks, man.
So again, resistance, the moment arm is 8 versus 5. And now we're going to do the same thing with the effort. So we have a similar conversation that comes up with the pull down, and I'm not going to belabor the point too much for right now because we've got technique stuff that we're going to get into. What I'm holding on to here actually is the effort, and all of that effort is going through this bolt here. Now, the one thing that changes this a little bit, and this is the point that I'm going to just brush on, is if I'm pulling, oh, hold on, that was dangerous. If I'm pulling at this angle versus this angle, it's going to change how the resistance, and it's going to change the effort. Because right at this point, if I maintain a perpendicular relationship to the ground and the axis, I'm going to have similar experience that I had with the pull down, where I've got this tangential relationship the entire time. If I'm kind of pulling down on this, it's going to change how much resistance I experience as an exercise user. So we'll get the dynamometer hooked up here and kind of look at that in a second. But for the sake of consistency, all of these measurements are going to be done with this perpendicular to the ground, parallel to the ground. So that way we don't make any big inferences there, if that's okay with you, for the sake of consistency. It's going to make my life a little bit harder. But what's nice about this is it makes it much easier to measure the moment arm, because you guys can see from where the effort is all the way up to this black peg up to these bolts. This big black bar is the lever arm. Well, in this case, this is the lever that is connecting these handles to that system. And it's weird, and this is one of the reasons why measuring a lever is not quite the same as measuring a lever arm versus a moment arm. This big metal bar is the lever. It is the piece from the engineering perspective that translates the joint axis to where the resistance meets this. The lever arm, which Tom has called the hidden lever, is actually, and we're not going to use this too much today, but for the sake of visualization, is actually the point of contact at the joint axis to the mechanism up here. So if we were actually drawing this in an engineering diagram, or we were examining this with some other visuals, this big black bar is the lever. And the reason why it's shaped for this big U shape is it actually allows this U shape to curve around all the other machines, right? How amazing that we've got this bar shaped to allow this pulley to sneakily go underneath it and never smack anything. The effects that we would measure if we were using a lever to measure the lever arm, and in fact, that's what we'll be discussing a little bit when we connect the dynamometer, is the point of from the joint axis to here. So we actually have a lever, measuring tape, arm, the lever arm, or the hidden lever, that in this case is actually going from here to here. Does that kind of make sense? It's kind of a weird notion, but the idea that you have mechanics, that is the lever, right? It connects the fulcrum to the point of application. That's fantastic, but you can actually strategically shape the bar to not interrupt the mechanics at all and get a different net effect with the lever arm. And we can talk about this more when we talk about first class, second class, third class levers and why those are interesting to learn about, but not super accurate, is because it's not always as it seems. Okay, so very quickly, we're going to collect the moment arms of these two pieces, and we're going to talk about it for a moment, then we're going to connect the dyno to it. So like Chris was saying, I'm going to connect, that's grease, that's fun. We're going to connect this right to that same joint axis, just for the sake of consistency. I'm going to do it on my side because it's a little bit easier to hold both of these together. And so if I keep this parallel to the ground and I measure this 90-degree relationship from the handle to the joint axis, I am getting 23 inches at the starting point. Okay. And then if I go to the extreme, this gets a little bit weird for me to measure. Actually, I can just do this. Beautiful. As long as I don't pull too hard and get smacked in the face. FYI, these are always much easier with two people when you're doing this crazy stuff. So if I measure that same distance from here to here, the effort is 16 inches. And so I've just flipped this around just to extend it, kind of like what I was just saying with you, Chris. Just so that way I get that same visualization. Cool, 16. Cool. So quick review of the numbers. And then we'll talk more about, we'll connect this dynamometer up and try to get some different data. At the first joint axis, we have a resistance with a moment arm at the starting position of 18 versus 11, plus the doubler pulley. So it's getting heavier at that first point in two ways. The resistance is doubling, and you have mechanisms, moment arm comparison, where the teeter-totter is heavier on the resistance side. As you go through that excursion, resistance drops off a little bit, but at the end of the first joint axis, resistance is still winning significantly and technically almost by double at the end of that. So you've got the doubler pulley and the resistance winning. So it's getting, right, so that 20 pounds, if you want to think of, this is not true, but it's a great way to start just thinking about it, right? The resistance at that first point, we have it being doubled. So I'm going from 20 pounds to 40 pounds. And then because the moment arm of resistance is nearly double, we could easily just say that now this first point, that's another 20 pounds. And now this first point weighs 60 pounds, right? The doubler pulley doubling it. And then we have that mechanism that's also nearly doubling the resistance, 60 pounds. I guess you could say 80, but we'll just say 60 to make it easy right now, because we're going to manipulate this a bit more in a second. So we've got this first joint system that's making it much, much heavier, right? In almost, it's 3 times heavier, if you want to think of it that way, 20 to 60. Now, if we come up to this first, the closer joint axis, where the human enters into the system, we kind of see the opposite, right? Resistance at the starting position was a moment arm of 8 versus effort of 23. Right, so we had that resistance that was 3 times heavier at that first joint axis. Now we have it switching, so effort is actually 3 times heavier, 3 times bigger than resistance. So now we're kind of getting this interesting, okay, it's got heavier 3 times here. At the starting position here, it's actually getting lighter by 3 times. So does that make it even? Right, does that help it break even? So that's kind of an interesting thing. And then as we go through the excursion, right, if we're already seeing that we've got this 3 times difference. When we go through that extreme excursion, we get all the way placed down on the ground, right? We're still seeing it consistent that effort has nearly 3 times. It was a resistance moment arm of 5 versus an effort moment arm of 16. Very interesting. So as we're going through this last moment arm, it does look like effort has a pretty significant advantage. And based off of just looking at these numbers, just looking at the data we've collected thus far, I don't see a massive change in resistance. There are some resistance properties that have changed because of the doubler pulley and then also the length of the effort for the resistance. But let's just have a look and see how the numbers change as we go through this. So what I'm going to do now, and this is what I was saying before to you guys, is I think it's a great academic exercise. I 100% endorse you to get on machines and try to look at these things. And if you get it or you don't get it, totally fine. Try to find those moment arms. Amazing exercise. I definitely recommend it. If you guys want to skip that step, take a dynamometer, hook it up with as best you can. Now, what I'm going to be doing here to make my life a little easier in full transparency is I'm connecting both of the input arms to this carabiner. So I've kind of got a V shape going on where each one of those arms have been disconnected from the prime handles, and I'm going to pull from here. So starting off with some tension, like the no tension really, this is at 0 pounds. So as I was saying before, we might see just from the starting position, it should be not really a huge difference. Which at this point, keeping it parallel to the ground, right? I was saying, I don't know if it's much of a big difference at the resistance and how much weight you're going to get, because we do have that 3 timesing of resistance, and then we've got the 3 timesing of effort. So at this point, while I'm holding it here, oh, sorry, got to hold it from here. This is 23 lbf. So we're not doing too bad, right? It looks pretty consistent that the number on the weight at this point, based off of both the data we collected and what we're seeing here, is showing that we should get close to a consistent number of 20. And we're just a little bit more than that. We can talk about some reasons why it might be 23. Actually, I have an idea and we'll try it. All right, so if I just hold it in the starting position, it is 23. If I come all the way back to the furthest position, now this gets a bit weird because what ends up happening, I'm gonna actually have to use a heavier weight. And the reason why, you guys can probably see, is the mechanism of the machine at this point, right? Where is it? You'll see it here, there. The mechanism of the machine has enough weight and moment that it's superseding the weight stack. So if I want to get the net effect of this, I'm going to have to use a heavier weight. So I'm going to go off frame for a second. Please bear with me so I can see this number. It's going to be a bit weird to do. Okay, so that's interesting. So same thing, that when I hold it at this point here, it is 60 pounds. But what's really interesting is as we go through this massive excursion, the increase in effort relative to resistance, decrease in resistance. As we go through this, we are getting a nice drop off through this, which is very interesting to see. And I do believe that part of it is all of the mechanisms, because if I'm holding this at this point here, it does start to drop off. But when we get all the way back to this back point here, the combination of the mechanisms of the machine and the effort, it's actually 24 pounds at this very back portion here. So very interesting to see that that's 60 pounds at the starting position. All those mechanisms are working, and it's pretty much at 65. As we go through the excursion of the exercise, it is designed that it looks like that all these things are lining up to help it make it be a lighter in the back position. And in this case, by about half, which is really a novel experience. And that's where I would definitely say, grab one of these dynamometers if you want to see what's happening when you're doing these exercises. This is an expensive one. When we're open, anyone that works here, you're welcome to use it. It's always on the gym floor. Definitely a very valuable exercise, very valuable thing. So what I wanted to see here, does anyone have any questions about that? I wanted to see something, right? So I was saying at the beginning, let's just find out. Yeah, it is, that's fun. Cool, okay. So it's pretty consistent. So this is a pretty interesting thing, is that what we were talking about with Liz's example, talking about the resistance curve, we are seeing that you're pretty strong out here because you got the mechanics and the muscle too. And as you come back, it would be nice to have a machine that drops off. In most cases, most cable machines, it's just a straight cable. Sometimes there's a doubler pulley in there. In most cases, there isn't. And you're just doing a straight pull, and it's really just a measurement of resistance. And now, in that case, with this traditional cable exercise, you're not seeing much difference in that it's going to be hardest in the back position, because as it gets further away from your joint, your elbow does in the resistance, it's heaviest at the back and lightest at the front, which is one of the reasons why you see most people performing a traditional rowing exercise where they're throwing the weight. Now, one thing that I think is an important piece to quickly talk about, depending on who is doing the exercise, is you got to talk about the machine. And there's two things that happen. So demographic wise, a lot of our clients that use our exercise machines are over the age of 50. And there's generally more women that come here than men over that age demographic. And so what we started to see is that this big metal bar here is the original trailing arm. It was the original piece that connected from here to here. This bar, right, there were two of them. Each one of these bars weighs 8 pounds. So it was starting to happen, right? I put my poor little Diane on here, who's 70 years old and probably one of the most frailest people that comes here. And this was at the very, very beginning. I just got this machine. Honestly, I hadn't explored the influence of the weight of the machines to be 100% on it. It was 6 years ago, I guess, not close to. And I put her on it, and I just saw her arm getting pulled down like this. What's going on? And then I grabbed the handle, and I realized I'd never experienced how heavy the handle was, because when I'm doing 170, 200, whatever pounds, the heavier weights are superseding the effects, as you guys just saw, of the mechanism and the machine and the heavier arms. It means that without even working, the machine was fighting itself based off of the weight of the organization of it. So if I have this machine that clearly, once we get to a certain point, is assisting beat the resistance, even as we saw with just the 20 pounds. And then you got 16 pounds of trailing arms that are stacking on top of that. That makes this a very uneven equation and makes it a very not accurate scenario for the exerciser, because they're not experiencing the resistance and the effect of the resistance machine. They're experiencing just the weight of the actual mechanism itself, which doesn't allow for consistency in the user. So what that turned into was two things, which gave us a lot of variety. As you guys have probably seen, if you've been here, I have our machine completely connected and hooked up with daisy chains. The daisy chains are rock climbing accessories that allow for different links in the system. And what's really nice about this is we get into the adaptation introduction of this, we're going to talk about strength to start. And then next week, we'll get more into hypertrophy supersets sets here, just using the one machine and positional stuff, is that these handles create a significant opportunity to manipulate where I'm experiencing the machine based off of the position that I'm choosing. Every time, and this is what I love about this. Now, unfortunately, to be frank, anyone that works here, you'll know that the position of this is kind of always set on that second daisy chain. And part of the reason is that, as you guys can see, the handles just sit here very conveniently. It makes it very neat, tidy, and orderly. But if we wanted to get some really interesting effects to the resistance and manipulate this, this changing in position allows us to get a strive machine style effect by manipulating the daisy chain without changing very much, without even changing the position of the handles. Very quickly, we saw that as this machine comes closer and closer down to this position, the resistance drops off significantly. So what ended up happening before, if we wanted, and to be honest, I don't think anybody here has mucked around with this, but if I wanted to muck around with getting that back portion of the profile, what I'd have to do is stand up and perform this exercise kind of like so I could get that full drop off. But I mean, it's a little weird, right? I wouldn't do this with clients because in most cases, having the pressure against the pad here to get that drop off in one way or another is not super comfortable. And it's hard to set up. I mean, for someone who's not stronger or heavier, manipulating your body around this, it gets a little risky, So if I wanted to experience a higher drop off for whatever reason, what could I do with these handles position wise to get more of that drop off?
Moving them forward on the loops, sorry. Making
Moving them forward on
the daisy chain shorter.
Yeah. So again, in this particular machine, but you can do this with almost a lot of different rowing machines like this. The more I move closer to the system, so I'll go to the fourth daisy chain here. And you guys will see it just gets a little disorganized on this machine because obviously it wasn't designed for it. But now what I can do, and now we haven't talked about positioning yet, which we will, because there's a big, a great exploration there for where you should be positioned. But now that I'm back here, you guys can see that I'm getting a much bigger drop off, right? I'm not at that starting position where I'm getting the same one-to-one relationship. I've actually got some of the drop off already happening because I'm halfway through the range. But as I come all the way back to this back position, I'm getting a larger drop off. That mechanism is closer there, closer to being at that end position. And if I really wanted it to be as light as I possibly could, I could move it more forward. Now that begs the question of, do we want a balanced profile or do we not want a balanced profile? So let's conclude today's discussion. We're not done yet, of course, but we're going to wrap up today's discussion talking about using this machine to try and develop strength, trying to work on maximal force output. And I mean that quite literally, not in a specific scenario, but how do we use something like this to get your upper back as strong as we possibly can? That comes down to a couple different things. We know that, and this is where we'll be talking about that in that little webinar, but if you just study neurological phenomenon associated with strength, arguably much more skill-based, right? If you look at power lifters, one of the things that you can see with Russian, a lot of the undulating periodization that the Russian teams did, that Louis Simmons does, and a lot of other powerlifting coaches do, which is very fascinating, is they perform the exact same movements many times in the week at a variety of different resistance levels. But in most cases, not all, but most, staying away from fatigue. Because when we fatigue, we start entering into that mechanical performance declination state, where you start seeing that the performance of the tissue starts to decrease. You're depleting the muscles of the substrates. You could be entering into that muscular mechanical damage section and start entering more so sort of into hypertrophy land. So theoretically, we want a couple things to happen here. We want to try to figure out where we want to get stronger. And I think a great place to get stronger, concurrent with powerlifting, is the weakest position. Because that kind of lines up with what powerlifting, strength sports really is about in most cases, not all, right? A deadlift, you're going to be weakest because of the mechanics at the very bottom position, and you got the biggest amount of resistance. So you want to get stronger at the position where you're going to have the least amount of force output. Bench press, same thing. That bottom position, you got the biggest distance from all the joints. Bench press, powerlifting, strength-wise is really about getting stronger in the weakest position. Same with a squat. So we can use the same mechanics here to try and line up with that. We want to try to increase output in the position where you are the shortest. Now, the question that arises, again, I kind of alluded to, is do we want to just go until we see some small performance declination of some sort, right? Are we measuring that from range of motion? That might be an okay place to start. Or do we want to push straight through that? So how do we set up this machine? So much like a Strive machine, what I've done is I've manipulated the profile so that way we have the carabiners as close to me as possible. So we know with this machine, if we stay at the top end of the mechanics of the machine, you're going to get the most resistance. You're going to get some drop off, but very small. And you're going to experience a lot of force at the end range position if you choose to experience and go to that position. So I don't have I'm not going to put a tremendous weight on here. I'm not going to go crazy with this here. I just got it at 65 pounds. But as we saw with the dyno, resistance stays pretty high. So this creates an excellent opportunity with this scenario that we're not getting the mechanics here super low to the ground. We're staying in a really heavy scenario. I don't need to max the weight stack out necessarily. And when I come all the way back to this position, I'm still experiencing a lot of force. And in fact, it won't be entirely accurate, but it should help. I'm putting this on the third daisy chain just so we can have consistency with the length. Yeah, that's 65 pounds, and this is 40 pounds at this point. So it's still staying pretty heavy, and we're getting the most amount of resistance out of this in this position. So we're going to just button this part up, and then we're going to talk more about muscles and positioning and forces of that next week, and how I think is a great way to do this exercise based off of all of the data we've got. So I've got it set up that's as long as possible. And if you wanted to use longer daisy chains, you could make it as such. But the whole idea with this to work on strength is you're going to come all the way back, try to experience that position at the back here as much as you can, fully embracing it, and then go out nice and slow. Now, there was something we saw last week that we got to really consider here. What happened on the eccentric portion of the exercise when we were doing these machines? What happened when we were doing last week's exercise machine on the eccentric portion?
We have to really control it going back because it wants to snap back.
Well, snap back. You got to control it. I don't know if I would use the word snap back, right? But you do have to
Okay, it
control
wants to.
There we go. Right? So when I pull on this 65 pounds at the 1 point, right? At this point here, well, I'm going to change this. It's going to be easier for me. Okay, as I start pulling this, this is 35 pounds, right? It's 39, 38, 30, 30, okay? So as I start going back, same tempo, 26, 33, 38, 37, 36, 30, 25, 26, 30. All right, what's happening here? 40, sorry, 39.3, 30, 25, 24, 28. What's happening on the eccentric when we do this?
Gravity of the lever arm pulling down.
Forget it.
Pardon me, Liz?
No, Chris had it.
Yes, we got a couple things, right? So to Chris, you have all the mechanics of the lever systems assisting, right? You don't have the friction of a lot of these pulleys working against you, because when you're yanking on this, all those pulleys are being squished with all that resistance change that's happening up to the machine, especially at that point where you got 3 timing that's happening. especially at the, and then you got the acceleration of gravity kind of going against you. It's actually trying to bring that weight stack down, which I think, Liz, that's what you may have meant. It's snapping down. So on the way back, you've got all these mechanisms that are trying, that really want that weight stack to go back to that starting position. And when you're yanking on this originally, you have to overcome all of those. You have to overcome gravity. You have to overcome the friction of the pulleys. You have to overcome all the mechanisms in the machine, which does provide small amounts of resistance, especially at lighter weights, which for clients, I can't express how huge that is. So on that same strength side of things, which is part of the reason why we're doing this, I mean, there's a decision when you're working with your clients, that, and this is part of the reason why the assessment we did on Friday is so important. Do you want to do this for all three modes of contraction, or are you worried just about one? Because if you're just worried about, okay, I mean, this is where it's been a long time, but when I've worked with a powerlifting athlete, we were just worried about the concentric for their upper back when we're thinking about deadlifts and squats. In that case, we were thinking about deadlifts. We were only worried about the concentric and how much force they could tolerate there, because when they were doing deadlifts, they could just let the weight go and drop, which is very different. So they don't need to worry about necessarily the eccentric portion of their upper back muscle. They just need to worry about maintaining that strength and getting into that position concentrically and isometrically. So if you wanted to, you could really emphasize that concentric by going slower, and stopping at the back there and not worrying about the eccentric as much. Or if you really want to work on getting the maximal benefit of the strength and resistance changes, as we talked about last week, slow down the eccentric, right? Come all the way in. You may want to come in a little faster, stop at the back, and then go out twice as slow, 4 seconds, to really experience more time under tension with that resistance on the eccentric end. Because as we can see, the eccentric mechanics and physics, why, is actually getting lighter and getting easier. And we know that from Brad Schoenfield and studying modes of contraction and pretty much any muscular literature talking about those three modes, eccentric can tolerate a heck of a lot more force. Well, we can't have more force, we can add more time that the system is under force. So next week, what we're gonna do is we're gonna come back to this machine, and I'll be honest, it's gonna be a little bit difficult with me doing this alone, just because it's easier when I have a model I can take through this. But we're going to talk about which positions we want to be in and why. There's some interesting, if you guys are on Instagram looking up exercise education things, there are some interesting camps, that are talking about sitting more forward and what you should do with the elbows, depending on what you're trying to do in the hypertrophy camp. I'm going to reconcile some of that data, and we're going to review those. Should be driving your elbows down to the ground. Should you be trying to bring your elbows all the way back? Should you be sitting more forward? Should you be sitting back? Are there risks or benefits to each one of those, which I think that there are? And then we'll talk a little more about hypertrophy and some practical drop sets here. I hope you don't mind for today. Anyone that's listened, as you can tell, I took a lot of things we talked about in previous weeks, and I tried not to belabor them. I tried to go through them a little bit more at a moderate pace. But I certainly don't want this to be just blowing over stuff that you want to learn about. Before we wrap up today, does anyone have any questions about this machine, the machine analysis, what we did with the dynamometer, anything that we talked about at all, anything that we can shed some light on, that you guys want to call me out on? Brandon, that was crazy. I feel that Brad Thorpe was up here, Mr. Isofit, and he gave me one of his Isofit hats. This is before we got super locked down. So I feel like it's ironic that I'm talking about dynamic stuff when I'm wearing an isometric hat, but oh well. Okay. Canadians, Strata family, thank you guys. I miss you guys so much. I hate that you guys are stuck on a 2x1 image. Americans, I hope that your doomsday scenario and your apocalypse goes well. Yeah. And send me a message tonight if you guys still kicking. And we'll talk to you. Okay, I miss everybody very much. And next week we'll talk more about practical rowing stuff. And if we button that up, we'll go into another rowing machine, because I think talking about chest support, it gets really cool. So thanks, everybody. Have a great one.
We miss you too.
Thank you.